SN2 reactions require good leaving groups. These are groups that are stable on their own, right? So in the past, we've seen chlorine and chloride and bromide. So these are very, very weak bases. They're able to spread that charge out a lot. So they're not strong bases. They're stable, low energy things. And so they're stable on their own. That's what makes them a good leaving group. So iodide is maybe one of the best leaving groups because it's the biggest. It can spread the charge out the most. Bromide is not quite as good, but still a pretty good leaving group. Chloride is okay, not great. Fluoride is terrible. Fluoride, bonds to fluorine are so strong that they're really hard to break. And so fluorine turns out to be a pretty bad leaving group most of the time. OH minus is also a bad leaving group. So I'm never going to just take an alcohol like ethanol and have some nucleophile displace that. That is not going to happen because OH minus is just too strong of a base, right? So it's too high in energy. So we need to do something about that. Your body needs to solve this problem because there are lots of cases where your body needs to take something with an OH on it and make that OH into a leaving group. And so we have different strategies to do that in the lab versus biologically. So one brute force way we can solve this problem is to add strong acid, strong in the 116 sense, so HBr, HCl, something like that. The reason for that is that when I treat this with strong acid, I'm going to protonate the oxygen. It's not a good base, but it doesn't need to be a good base to do this. And then I'm going to end up with an OH2 on the end of this, and a Br minus. So now my leaving group isn't OH minus. My leaving group is water. And you may be familiar with water as being a pretty stable and prevalent molecule. So once this is water, now bromide as a good nucleophile can easily come in and displace it. And that is one way to have OH be a leaving group. The downsides to this approach are obvious, right? I probably don't want to be sloshing around hydrobromic acid or hydrochloric acid every time I want to change a bond like this. Your body certainly can't do that, right? I can't just have a whole lot of HBr everywhere. And so this is a kind of a good brute force method, but we'd like something a lot less acidy to solve this problem more generally. Let's say I don't want to use strong acid all the time to do this, because I do not. Another way that we can do is to turn the OH into a sulfonate. Sulfonates have a sulfur with 3 bonds to oxygen, 2 double, 1 single, and then a bond to carbon. Remember, sulfur with 4 bonds to oxygen would be sulfate, SO4. This is SO3. So the most common sulfonates are tosylate for purely practical reasons. This is the cheapest, this is the easiest to work with, beautiful white crystals, etc. Mesylate is another one with a methyl group here. It's a simpler molecule, but it's more expensive, and it's a liquid, so it's a little bit more of a pain. But in general, reactivity-wise, both of these are going to do what we want them to do, which is turn OH into a good leaving group. Here's how it looks in practice. I'm going to take this alcohol, and I'm going to treat it with something I'll call tosyl chloride. This has a sulfur-chlorine bond in there, and then some weak base like triethylamine. The mechanism of this is really more organic 2 material, but you can kind of imagine that I've got a nucleophile and an electrophile as well. And so I'm going to have this new piece here. Now my oxygen is part of a good leaving group. This is a tosylate, sometimes abbreviated OTS. And yes, when there was a new element with the TS abbreviation, that made me a little bit upset. But that's okay. For stuff that people care about, TS will always mean tosyl and not tennessine. Anyways, here's my leaving group. When I treat this now with any good nucleophile, like sodium bromide is fine, don't need HBr anymore. This can do SN2 really nicely to give me this. And here's my leaving group, and now maybe you can tell why it's a good leaving group. I can take that negative charge and spread it out over all of these oxygens. So this charge is resonance stabilized, which makes sulfonates like tazolate or mesylate very good leaving groups. So again, it's 2 steps instead of 1, which I don't like, but it avoids the use of really, really strong acid, which A, is dangerous, and B, is probably going to mess up my reagents and reactants in other ways, right? So you don't fix stained glass windows with giant sledgehammers, and you generally don't use strong acids to do your SN2 stuff. Make it into a tazolate. Let's talk about biology. So here we've got biological leaving groups. Your body does not use HBr or HCl most of the time to make something into a leaving group. There is not tazol or mesyl chloride in your body. What there are things that are going to make phosphates. So phosphate, you can kind of see, is similar to that sulfonate that we saw, right? In both cases, what we're going to have here as a leaving group is oxygen that's going to be able to spread its charge a little bit into that phosphorus-oxygen double bond. So again, a resonance stabilized leaving group. So your body does a lot of work turning OHs into phosphates and diphosphates. Diphosphates just with 2 phosphoruses there. The enzymes that do this are kinases, and they use ATP. So here you go, adenosine triphosphate. So if you've ever taken a biology class at any level, you've learned that ATP is the energy of the cell, right? Well, what do you mean, energy of the cell? What does that actually mean? Here we go. By energy of the cell, what I mean is that I'm going to make chemical reactions possible by making this OH into a decent leaving group, right? So that's a bad leaving group, that's a good leaving group, and the enzyme kinase is doing the job to take this piece from ATP and essentially staple it onto that OH. Okay? So that's what ATP does. That's why it is the energy of the cell, is that it's a way to make a good leaving group. It is essentially the biological version of tazol chloride, if the way is the way that I think about it. If you want to think of tazol chloride as the lab version of ATP, that's great too. They're both cool. Another really important biological reagent, so to speak, is S-adenosyl methionine, or SAM. Methionine is this piece from the sulfur over, that's a common amino acid. Adenosine is the same piece that's in ATP, the circled piece. And notice it's got an extra methyl there. That's what's actually going to do the job. So some nucleophile can come in and attack the methyl. Again, methyl is almost completely unhindered. Those little hydrogens don't really matter. And so this is going to be a great SN2 reaction. So what's my leaving group? My leaving group is this whole thing. So everything in SAM except for the methyl group, you could really think of as a leaving group, right? And it's a pretty good leaving group because it's stable on its own, right? Once I break this SC bond, that sulfur already has a positive charge. So here, these electrons are going to go back onto sulfur, and now sulfur is a nice, stable, bivalent, neutral molecule. So this adenosylmethionine is pretty stable on its own, which makes this whole piece a great leaving group. This is how your body is going to methylate stuff that needs methylation. So if you've heard about DNA methylation, important in epigenetics, this is how we can think about the body controlling DNA methylation in our cells. To recap, leaving groups should be stable on their own. Most of the time, we're going to have halides as our leaving group. They're really good at this because they can spread that negative charge out. Another important leaving group is the sulfonate. Again, they can spread that charge out among many oxygens. Those are attractive because we can turn alcohols, which have bad leaving groups in OH, into sulfonates, which are good leaving groups. We can also just think about neutral molecules, right? So when we use strong acid, water was our leaving group, and water is pretty stable. Biological examples of this are phosphates and diphosphates, which we get via ATP, and the enzyme classes called kinases. And we can also use stuff like SAM, S-adenosylmethionine, to show methylation. And again, the leaving group there is just a giant neutral molecule, adenosylmethionine. So leaving group, stable on their own, important for this reaction and others that we'll cover this term.